Okay, so I think we should be live now. Let me check on the chat. Okay, yes, they can hear us. Great. So,
Okay.
okay, so it's my pleasure to introduce Abhinav, who has been very kind in accepting this invitation to give a presentation for us. He's working now as a professor to the University of Freiburg, and he will give a talk about his research on cognitive robotics. So just one note, guys, if you can keep track of the slide number if you ask questions, and you can refer to that, maybe it's a good idea. So you should be able to see the slide numbers during the presentation. This said, then Abhinav, take it away. Thank you very much again.
Thanks, Roberto. Hello, everyone. My name is Abhinav Valada. I'm an assistant professor and I head the Robot Learning Lab in the University of Freiburg. So today I'm going to talk to you about some of the research that we've been doing in Freiburg in the area of perception mostly, and how we are now going towards more including learning actions for perception. So let's get started with a very brief discussion on why this research is important. So today we have more robots now than ever in our world. However, as you can see, most of these robots operate in fairly constrained environments, such as in industrial spaces where these robots perform repetitive tasks. We also have robots delivering food nowadays in hotels, and of course in factory warehouses. But in more complex domains such as medical surgery or space exploration, these robots are often teleoperated or they are pre-programmed to perform specific instructions. And of course, we all have our favorite cleaning robots in our homes, which are, as you can see, the self-driving vehicles of our pets. Now, I'm sure these are not the only ways in which we all envision robots to be used in the future. So what we envision for the future is robots to be performing tasks more like these. And as you can see, these environments are no longer contrived spaces. So we want the next generation of robots to be performing far more complex tasks in unknown and unstructured environments, as well as in shared spaces with humans, such as in transportation settings and precision agriculture, robots in disaster scenarios, robots helping in household chores, and so on. So in order to achieve reliable operation in these immensely complex environments, we must enable robots to learn and adapt to unexpected situations to facilitate reliable long-term robot applications. All right, so I think most of you might already know this, but let's briefly look at how typical robotics pipeline looks like. So in the case that you see here, it's illustrated for autonomous driving, but it's similar for, say, a grasping task. So robots often have multiple sensors to perceive the environment around them, such as cameras, lidars, and radars. And the observation from these sensors first go into a perception and state estimation module, where, for example, this enables a car to identify the surrounding traffic participants in the environment and localize itself in a pre-existing map. So these localized traffic objects then go into a modeling and prediction step, where where we basically predict where each traffic participant is going to be in the future. And this will then be a motion planning module to plan a safe collision-free path. And these plans are finally executed by the controller. So now if we think about the representations that are classically used in these modules, let's say about 7 years ago, so these consist of explicit handcrafted descriptions of the environment, such as SIFT and HOG, for example. So not only are these descriptions extremely hard to compute in the real world, they do not often generalize to complex real-world environments, such as that you see here, where we have a diverse range of objects that are often occluded, or in outdoor scenarios, we have many dynamic objects that have complex interactions among themselves. And in outdoor scenarios, these environments themselves undergo appearance changes due to weather, season, and so on. So this is often the primary bottleneck in why these systems fail in the real world, and this very naturally motivates sort of learning-based robotics. All right, so if we look at the current learning paradigm that we employ, we can see that it's quite narrow in scope. So how does this learning happen in most other fields, and how does it differ from robotics? So the first step that we do is we collect a large-scale data set that we train our network on. We use it for a task, and then we forget about it. Then we train another network for another task, and so on. So if you think about this, this is not really scalable when it comes to robotics, where we need to learn many diverse tasks for multiple environments that we often do not have labeled training data for. And this is especially not scalable in robotics, where we need to learn multiple tasks. So moreover, state-of-the-art deep learning architectures consume a significant number of parameters, and they have large inference times, which makes them to be infeasible to be useful in real-world robots that often have very limited computational resources. And so since we want the next generation of robots to be performing tasks in unknown and unstructured environments, these models should effectively generalize to, say, previously unseen scenarios or environmental conditions. So this is essentially what motivates my talk today. So in this talk, I'll first briefly talk about deep learning-based approaches that enable a robot learning system to robustly perceive and localize itself in the environment. Secondly, to dynamically self-adapt these models in adverse conditions, leveraging multimodal data. Third, to simultaneously learn multiple diverse tasks while reusing and exploiting complementary information. And now these techniques together enable robots to operate in diverse real-world environments and operating conditions. Now the road doesn't end here, right? So the key to further scaling up learning is to extend these methods to learn, say, in a self-supervised manner by closing the perception action loop. And I will talk a little bit about this towards the end of this talk. All right, so let's get started with the first work here. So mobile robots in particular encounter a wide range of terrains while navigating in an environment, and they are required to be able to distinguish the different terrains that they traverse on, say, for example, to determine the corresponding trafficability. So as we see here, the predominantly adopted vision-based approaches are highly susceptible to failure due to the very similar visual appearance of these terrains. Now, potential solution to this problem is to leverage proprioceptive modalities such as vehicle terrain interaction sounds to classify terrains. So here you can see some examples of different kinds of terrains and the corresponding spectrogram representation from the vehicle terrain interaction sounds. So this was basically collected with a P3DX robot that you see here, with the microphone that was attached very close to the wheels of the robot. And we basically have, I think, 3 indoor terrains, and the rest are outdoor unstructured terrains. Right, so to address this problem, we basically proposed a CNN-based approach in which we first transform the vehicle terrain interaction sounds to the spectrogram representation, which is then input to our network for feature learning and classification. So our network here basically consists of a number of convolutional layers, and we propose this module called global statistical pooling. So this module basically combines 3 different global pooling strategies. So normal L2 norm pooling, global L2 norm pooling, average pooling, and max pooling together. And then we combine all these features and then pass it through LSTM unit. And then we have a bunch of fully connected layers in the end. So here we demonstrated that a network achieves state-of-the-art performance compared to classification using conventional audio features that are often used for speech processing or sound analysis. So what's more important here is that as in real world environments, we have a substantial amount of noise. We propose basically a noise aware training scheme where we randomly inject ambient noises from a noise database, and we regularize the network to be more robust to real world ambient noises. So here we basically see that we show that we basically achieve over 8.83% improvement compared to state of the art speech features, for example. All right, so in addition to being able to identify the different types of terrains, robots also need to understand what the different objects in the environment are in order to plan future actions. And we can basically formulate this as a semantic segmentation problem, where the goal here is to assign semantic class labels to each pixel in an image. So for example, this is the output of the network. And here you see that the colors of the pixel denote which semantic category that the pixel belongs to. So for example, here blue pixels denote cars, red pixels denote persons, gray pixels denote poles, and so on. So there are a number of challenges for semantic segmentation for natural scenes. So let's briefly take a look at them. So primarily pooling and striding in CNNs reduce the spatial resolution of the feature maps at the output of the encoder, which often removes the details on object boundaries and thin pole-like structures. And objects and images of natural scenes also appear in multiple scales, such as nearby objects appear larger and faraway objects appear smaller. So your network needs to be able to capture objects of multiple scales. And as I mentioned before, most state-of-the-art architectures consume a significant number of parameters. And if you want them to be useful in real-world robots, we have to make them substantially efficient. So considering these challenges, we proposed last year our AdapNet++ architecture that provides effective solutions to these problems. So our network here consists of an encoder that's basically based on the standard ResNet 50 architecture. But here we propose novel multi-scale residual units. So what we do is that if you're familiar with the general residual net module, we add parallel at-rest convolutions or dilated convolutions in parallel to the standard convolutions with different dilation rates. And this enables a network to learn multi-scale features throughout the network without increasing the number of parameters. So now in order to further learn multi-scale features and to capture long-range context, we proposed a module called eASPP, or the Efficient At-Rest Spatial Pyramid Pooling module. So this, you can think of this as a variant of the standard ASPP that was proposed by Google a couple of years ago. So now our eASPP transforms the standard ASPP architecture into a more efficient structure by leveraging the bottleneck topology and by cascading at-rest convolutions. So now the bottleneck topology basically makes our eASPP 10 times more efficient than the standard ASPP. And by cascading at-rest convolutions, it enables our network to have a larger effective receptive field than the standard ASPP. And this also improves the performance of our network. So in order to illustrate the effect caused by cascading two at-rest convolutions, let's visualize the receptive field here for the pixel annotated by the yellow dot. So here we see on the left the receptive field of the standard ASPP and the receptive field caused by cascading at-rest convolutions in our proposed eASPP. So as we see, our eASPP is able to capture much larger context, such as the entire bus in this example. And this enables us to not only reduce the number of parameters, but also improve the performance of our network. So now, at this stage, the output of our network is still 16 times downsampled with respect to the input resolutions. And we need to upsample these feature maps to get the same resolutions as the input. So for this, we proposed a new decoder topology in which we have 3 upsampling stages, where each upsampling stage we upsample by a factor of 2 using deconvolutional layers. And then the last stage, we upsample by a factor of 4. So we also fuse high resolution features from the encoder into the decoder for object boundary refinement. So we benchmarked this on a couple of standard benchmarks, Cityscapes, which is a very popular outdoor data set, Cynthia, Sun RGBD, and ScanNet are 2 indoor data sets, as well as our own unstructured environment data set, which was collected here in Freiburg. So here you see very quickly some qualitative results. As you can see here, visually, our network performs equally well in indoor environments as it does outdoors, as well as in unstructured natural scenes. So now this enables robots to truly understand the world around them without requiring, let's say, specialized architectures for each environment. So here you see the leaderboard standing. I think this was sometime in the summer last year. So things in scene understanding changed really quickly. So this is not the case anymore. So our proposed network was 6th on the Cityscapes Leaderboard. But as you can see here, that our network is still the fastest among the, and was fastest among the first entire approaches in the first page of the leaderboard, and we're also the most efficient in terms of the number of parameters that we use. So this enables us to use the model in real-world robotics applications.
Sorry, Abhinav.
Yeah.
We have a student asking if you can explain again the eASPP details.
Yeah, maybe it would be easier with another slide, but I don't have it here. So basically, if you're familiar with the standard ASPP, the standard ASPP has basically just one convolution, one dilated convolution on each of these 4 branches, and then the last branch is basically global pooling. So, and they use different dilation rates in all of these. So what we did, instead of having just one dilated convolution with 3x3 filter size, we did a bottleneck topology. So what a bottleneck topology is, similar to the ResNet residual units, where you have 1x1 convolution, 3x3 convolution, and 1x1 convolution. So you first use the 1x1 convolution to reduce the number of filter layers to, let's say, from 128 to 64. And then you apply 3x3 dilated convolution on the reduced number of filters. And then you upsample these feature maps. Then you again increase the number of filters to 128. So by doing this, instead of employing dilated convolutions on a large number of filters, 128, here we only do it on 64 filters. And the other thing that I said is that instead of using one 3x3 convolution, we use 2 3x3 cascaded convolutions. So this makes it basically I don't know if you can see my mouse pointer here. So this would be a 1x1 convolution. These two would be 2 3x3 convolutions, dilated convolutions, and again 1x1. And now these parallel branches each have different dilation rates. For example, 4, 16, and 32, for example. And this would be global pooling. So by doing this, we not only reduce the number of parameters by bottleneck topology, by cascading, we get a better performance. I hope that was understandable. Okay. All right. So, okay, so I think I was here. So on the ScanNet leaderboard, we were basically 3rd at that point of time, but we were still fastest network on the leaderboard as well as most efficient. And yeah.
See. Okay. So we have some more questions. In particular, we get the question, why didn't you use an image approach for the terrain categorization?
So the thing that I'm going to talk about in the end is also using the image approach. So I would say the main motivation here was that, we kind of want to use all the modalities available that's there in a robot. So images are primarily, or images or LiDARs are primarily what you would want to use for planning, because you need to see what's ahead of you, and you need the robot to basically categorize terrains that are ahead of you to know to plan future actions. But then if you think of it, visually it's really hard to visually it's really hard to detect very let's say terrains. If I can go to the slide, terrains such as grass and mowed grass, or for example cobblestone and asphalt, because they have very similar textures. So as you can see on the slide, so yeah, so many of the terrains have very similar textures. So often mowed grass looks very similar to grass, and if you want to classify both of them, then you will kind of have problems. Also, asphalt has very similar sort of appearance to linoleum, for example, or carpet, as you can see here. So what we wanted to do in this work was basically, can we use some other modality that is more robust or does helps in learning these sort of different kinds of terrains. So one thing that you note with proprioceptive classifiers is that they can only classify terrain once the robot is basically on this terrain, right? So you can't classify what's ahead of you. So you can only classify what's near you. So you can use this in conditions such that if there's water, for example, and your robot, you don't want the robot to go on water, right? So if it just touches the water, then you can know that, okay, I shouldn't be going close to here. But towards the end of this talk, I would basically talk about a self-supervised learning technique where you can use this audio-based proprioceptive classification to learn a visual classifier about what's there ahead of you. And I think that's like more about like say going towards lifelong learning, where you can just make your robot roam freely in the environment, and by just hearing what's around it, it can learn to understand what's there in front of it.
Okay, so they're asking how well this approach works when you are in noisy environments.
So I think the last numbers that I remember was around 84%. So I think 86 was in a clear environment with normal ambient noise. With normal ambient noise, I mean that, there could be a person now and then walking around, but not like in a densely crowded, say, middle of the city. So in order to do densely crowded middle of the city, then we propose this. So there's this database of noises, or like ambient noises, which is called the demand database. So what we did is that we sampled random noises from this demand database. I think it's over like 12 hours of different ambient noises. And then we inject these ambient noises like into the clean noise samples while training. And we also do other kinds of noise augmentations. But this helps us regularize the network to learn better features, and also helps the robustness in real world environments. Okay. Let me go back to the slides. All right, so here, if the video plays, okay, so here we see some results on the Cityscapes dataset. We can see that our network is able to accurately segment objects of multiple scales, such as nearby cars and faraway cars. We can also see that our network is able to segment thin objects such as poles, as we see here. And our network is also able to accurately segment object boundaries, such as trees, as well as other categories, as you see here. So there's a live demo on this link. If you go here, you can see it's basically deepscene.cs.uni-freiburg.de. And you can see the performance on different indoor datasets and outdoor datasets. Okay. So we also did real-world navigation experiments because in the end we want these to be useful for robots. So here you see a Viona robot here that autonomously traversed over 12.5 kilometers from the city of Freiburg to reach the top of this mountain, which is called Schauinsland. And here we only use the segmentation for perception. So we have other sensors here, but in this basically expedition, we only used the segmentation, um, and here I think we didn't have to do any human intervention other than the fact that once there was a random dog that came in front of the robot and it wasn't basically moving, so we had to stop the robot for a while. But other than that, um, the whole perception system was quite robust. So more recently, we also used a version of this network to localize the robot. So what we did here is that we used the same network basically, but here we want to predict room layout edges. By room layout edges, we mean that the corners of the room, the bottoms, and the part that intersects. So basically the red lines that you see here predicted by the network. And we use this information to localize the robot, the Festo Robotino that you see here, in a given floor plan. And we do this using a particle filter that basically matches the predicted edges from the floor plan. Predicted edges from the network to the floor plan. So the input to our network here is basically an RGB image, and we detect vanishing lines. So and we do like basically traditional image processing to detect vanishing lines. So what vanishing line tells you is that if you assume a Manhattan world assumption where you have three axes, then you want to detect edges or lines in each of these axes. So in the figure that you see here on next to the RGB image, so the red lines are basically on one of the axes, the blue lines is on another axis, and the green line is on another axis. So we predict these vanishing lines and we overlay them on an RGB image. So this is the overlaid image, and we input this to our network, which then predicts basically where the edges of the network could be. So in the video that you see here, the layout edges predicted by the network is shown in red, and the layout edges that we obtain from the floor plan using the current Monte Carlo estimate as the base pose is shown in blue. So now the network here was never trained on this environment before. It was only trained on the standard LSUN benchmark, which contains multiple environments. And here our network, I think it's still the state of the art on the LSUN benchmark. So now the models that I just described provide effective solutions to some of the most fundamental challenges in each of these tasks. And they perform really well on benchmarks as well as real world environments while being compact and having a fast inference time. So next we will go into the next topic, but should we take some questions if there's any?
Yes, so there is a question. Why door edges are not predicted?
Why? Pardon me?
Door
edges.
Door edges, yes.
Because in layout estimation, generally windows and door edges are not, it's not a part of this task. So it's useful for localization. So there is some work that that also predicts basically the frames of doors or the frames of windows, but it's not considered a room layout. A room layout is basically any structure that intersects the walls with the floor with the ceiling. So that's generally how the task is formulated. But if you also predict let's say outlines of windows or doors, that also helps to further improve localization performance. And here, if I think forgot to mention maybe, so we have, I think we on the floor plan we achieved the localization error of 22 centimeters and 2.5 degrees.
Okay, so I don't think we have other questions for the time being.
Okay, so let's move on then. So nevertheless, state-of-the-art models, even though they perform really well on all of these benchmarks, they still face several challenges in the real world. Where they demonstrate significant misclassifications, primarily due to visual appearance changes caused by changing seasons, lighting changes from day to night, adverse conditions such as rain, fog, and so on. And here you can see the image on the left is basically right outside our campus here, that our network basically misclassifies the decal on the train that you see here as a real person. And we also get a substantial amount of misclassifications when we have over or under exposure of the camera. So these scenarios basically show that perception in the real world is extremely challenging. So how do we improve the robustness of our models in such situations? So an approach to tackle this problem is what we can do is to exploit features from complementary modalities such as depth and infrared, and to fuse these features with visual RGB information, because from depth and infrared, we can exploit object properties such as geometry or reflectance. And by this, we can enable our model to be more resilient to challenging scenarios. Now, there are several challenges to multimodal fusion. Basically, most of the work in deep learning primarily focused on where to fuse these features, such as early fusion, that is on the beginning layers of the network, late fusion, or hierarchical fusion, and so on. So, however, there is evidence that the human brain basically performs late fusion, which means that the fusion of features occur at the semantically higher level. So, but there's very little work that's basically done on how to fuse these features. So I think the earliest works that I know of was maybe from 2018. But most existing architectures or approaches for multimodal fusion naively combine the fusion. And by naively, I mean that they directly add the feature maps or directly concatenate the feature maps. And the problem with this is that the fusion of features is inherently complex, and the fusion depends on several factors, such as the semantic object categories present in the scene. For example, in one scene, you might have like grass, unstructured terrain, forest. In another scene, you might have like asphalt, buildings, poles, and so on. And so which modality to use really depends on which modality works well for one semantic category that you're interested in. And it also depends on the spatial locations of objects in the scene. For example, if you use depth modality, depth is really good for nearby objects. But as you go further and further, your depth perception basically like degrades really quickly. So you want to use depth when it's accurate, which means for objects that are closer to you. And then for objects that are farther away, where you don't have much information, you want to still rely on RGB modality. And in the example that I just described before, for example, in situations that you have under or overexposure of the camera, you need to be able to detect these situations and change based on the context of the scene. And by directly adding or concatenating these features, we don't enable the model to adapt to these scenarios, because you can't predict from the beginning what these situations are going to be in the environment. So you need a model to dynamically adapt to these changing conditions. So I don't think we have enough time to go over the entire architecture in this talk. Maybe in the end, if there's still time, I would describe more in detail. But here, what we basically proposed is this module that's called Dynamic Model Adaptation Unit. So I would briefly explain how this works with an example. Let's say that we have two streams. So we want to do late fusion, which means that we have two encoder streams, an RGB stream and a depth stream. And by encoder, I mean you can take a ResNet architecture or any standard classification network. So if we visualize the features, say for this image that you see here, and let's say we are interested to segment the bathtub class. So we visualize the features individually from the RGB stream and the depth stream. Here we have HHA encoded depth, which is another form of encoding of depth, but let's just assume it's normal depth. So as you can see here that the networks for individual modalities give you substantially noisy activation. So we have noisy activations which are on one modality. In other areas, we have noisy activations from the other modality. So what we do now is we concatenate features from these two individual modalities at the semantically high level, which means towards the end of the encoder. And we then pass these through our module that you see here at different parts of the network. And what this module does is that basically it emphasizes on the more stable features in one modality and de-emphasizes the stable features in the other modality. And it does so by generating weights from a sigmoid function here dynamically. So these weights, although the weights of the convolutional layers are learned, but the weights that are multiplied from the sigmoid are generated based on what the different conditions are. And then, as you can see here, at another stage after the fusion, we have more stable features only on the more stable activations, only on the object that we care about. And then we get the corresponding segmentation. And we can see here that we're also able to segment around objects that are placed around the bathtub here. Okay, so we once again benchmark this on the same 5 data sets that we did our unimodal approach. Cityscape, Cynthia, ScanNet, SunRGBD, and Freiburg Forest, in which we achieve state-of-the-art performance for multimodal semantic segmentation. So on the bottom here, what's interesting is that on the Cynthia data set, you basically have different seasons and weather conditions. So this data set is really good for evaluating how robust your model here is. So here we trained a model only on RGB images, and we evaluated them for multimodal fusion on different seasons and weather conditions, as you see here. So here you can see on red, the comparison of the model basically only trained on RGB. On blue, you see the comparison of the model only trained on depth. And on green, you see the comparison of the model after RGBD fusion using the approach here. So as you can see, with RGBD fusion, we are substantially better than using any of these individual modalities. So I think what's more interesting is that it makes these models more robust to these adverse conditions, which we see a bit later in the qualitative experiments. So once again on the Cityscape.
So, excuse me, can I interrupt you? We have a couple of questions. So first of all, I think this is related to what you were talking before about the localization in the rooms, which is how was the dataset used to train the CNN generated in order to predict the edges?
Okay, so what we basically do is that so the network basically predicts. So the input is, as I said, it's an RGB image, and the vanishing lines overlaid on the RGB image. And the network now predicts a Gaussian along the layout edges. And then we threshold the Gaussian basically at some fixed threshold at the output that then gives us this binary map. But the network actually predicts a Gaussian from 0 to 225 say the highest intensity would be, you know, exactly along the edge, and then it will start spreading out. So, and then we threshold it based on how thick we want the predictions to be, and that's what the network predicts. So the actual data set itself that Elson provides just gives you basically the corners of like, you can think of it as key points of the corners where the floor and floor, wall, and the ceiling meet, and then we can basically draw lines if we know the topology of rooms.
Okay, thank you for the answer. Then we have another question, which is, I think, on the last topic we were talking about, which
Mhm.
is if you could explain a little about the some implementations details, like for example, how many layers you have used, what is the accuracy, and so on and so forth.
Okay, so basically what we did here was that the previous network that I just described for using single modality segmentation, so which was AdapNet++. So what we did is we took the AdapNet++ architecture. Maybe it's easier if it's again only a schematic because it's um, over 80 layers, I think. So it would be hard to describe the whole structure. But so this was a single modality architecture, as you can see. So what we did is that at the end of our eASPP here, where the feature maps are the smallest, here at this location, as well as in this two locations where we take the skip connections, we add our model adaptation unit. So we have two streams, like one stream and another stream, where each stream takes one modality as input. Then the feature maps at these two locations, as well as the end of the encoder, are fused with this model adaptation unit. And then the fused feature maps then go to the decoder here. So if you want details in terms of how many layers, I think that would be super complicated to explain in the start, but the basic principles works like this. So if you take a look at the paper for AdapNet++, you can, there's details on like what each layer's parameters are, and the code is also available online. Mm-hmm.
Okay, so yeah, we have one more question from the same guy who is asking,
Mm-hmm.
can we use a GAN network instead of this architecture?
That is a good question. So the problem with GANs is that it's really, really, really hard to train, right? Um, and when you have labels, there is no reason to use a GAN because it's not going to perform better than supervised training. So GAN is usually useful when you don't have labeled training data that you want to train, you know, in an adversarial manner. That being said, there are some approaches that basically try to do this, but I think they're more um, proof of concept that it does something rather than they're nowhere close to supervised approaches. But you could do it also. Okay, I forgot where we were. I think Cityscapes Leaderboard. Yeah. All right. So at the time of publication, we were third on the Cityscapes Leaderboard. Well, you can see that our network is still faster than the first two methods. The first one here, I think, I forget who's it from right now. The second one is from Google, and the first one was again another company, I think. And on ScanNet, we were basically first. I don't think we're first anymore, but we were also fastest compared to other networks on the ScanNet Leaderboard. All right, so now I think what's interesting is to basically look at the performance in challenging scenarios, right? So here you see some scenarios such as fog, rain, and snow. Here we train our model only using RGB images, and we deploy it using RGB diffusion. And as you can see, it's almost indistinguishable that a model performs equally well in fog as it does in rain and snow. But if you see the images here, just the RGB images, it's even hard for us humans to see what is really going on in the rain, for example. Whereas a network here can leverage the most stable depth modality to give you accurate perception. And once again, on this website here, deepscene.cs.uni so there's code for all of this online, as well as live demos on various different data sets. Okay, that I think brings us to the third part. If there's any.
Okay, so yeah, we have a question and then I think we can have a break, 10 minutes
Okay.
break. So the question that we have is a guy who's commenting, I have seen that the localization using the edges in the video is 10 times faster than real time. Is this method slower than the other monocular SLAM methods?
So I don't remember the numbers off the top of my head, but the video was just made faster because it's boring to see the robot move slowly. So if you take a look at the paper, I think we have computational analysis, but the network really doesn't take time, right? So the network predicts, I think we only take a 224 size input, so which takes like 9 milliseconds, I think. So I think the other stuff like, so if you want to find the edges from the floor plan, then you have to do like raycasting on the floor plan, project it back to the image. So those take more time because they don't run on the GPU, but you could make it faster. But for the exact numbers, I would say take a look at the IROS paper where we have like plots based on which component takes how much time.
Okay, then let's have a 10 minutes break now and then we'll resume in 10 minutes.
Okay,
Thank you.
thank you.
Okay. Okay, so guys, we are restarting right now. We have a question actually, Abhinav, which is, in order to get the depth information, have you tried different sensor? And if yes, I mean, does this change any of the results that you got?
Yeah, so significantly it does. So different data sets that we benchmark on itself use different sensors. For example, um, indoors, I think all the indoor data sets primarily use structured light sensors like Connect or ASUS, Xtion, or whatever. And all the outdoor data sets, I think they all use stereo cameras. And I think actually Kitty uses LiDAR, but I think for this work we only use the stereo. So it does make a lot of difference. We found that multimodal fusion using depth, you see a significant improvement in performance on indoor data sets. That's because that indoors you don't really have scenarios often that are, um, where depth is bad, only in the case that, depth, the room is like massive or something like that. So in normal scenarios was where it's an average room, then the structured light sensors work pretty well. And outdoors, of course, you can use them. So you have to use a stereo camera if you want to use depth. And in those cases, you don't get so much improvement when depth is like not really accurate for faraway objects. All right. So now, in order to truly develop large-scale learning systems, especially as in where we have robots, where we have an ensemble of modules contributing to the autonomy, so we need to make our models to learn to. We need to make our models to effectively reuse and share information across different tasks. And so we've done quite a bit of work in context of multitask learning. In this talk, I will briefly speak about one of them. So for robotics, it's not only essential to know what the objects in the surrounding are, we would also like to know if the objects in the scene are static or moving. So if we apply some reasoning to this image that you see here, we can probably say that the traffic light is green. So all the cars that are towards the center of the road are probably moving, right? So now, if we look at two consecutive frames, we can see that the car in the center is actually static, and only the car on the left is moving. So therefore, there are several scenarios such as these where we need to explicitly predict if the objects in the scene are static or moving for safe operation of this robot. So currently, most learning methods tackle these two problems disjointly or independently. And in this work, we were basically interested to see, are there any actual benefits in learning these two tasks jointly? So it turns out that there are several benefits in learning both semantics and motion estimation together, as each of them provides complementary information. So for example, on one hand, we can say that the transition in motion will always occur on the dynamic object class boundaries, such as car and people. The transition in motion will never occur for objects that don't have the possibility to move, such as buildings and poles. And the semantic object class itself provides important cues for predicting the object motion. For example, the probability of a car or a person moving is greater than a building or a pole. And semantic cues also encourage temporal consistency across time, because the semantic identities of these objects are consistent between one frame and the other. So there are several challenges to this problem, such as ego motion of the robot itself often causes discontinuities in the optical flow magnitude. Varying pixel displacement, such as nearby objects have larger pixel displacement and faraway objects have smaller pixel displacement, lighting changes between two consecutive frames, and so on. So again, this is like a smaller schematic of the actual network, but I will briefly go over the network that we proposed here, which is called SMSNet++. So basically, we once again built on top of our AdapNet++ architecture, the first one that I described. So here we have the stream that is shown in green learns semantic features, and the stream that's shown in green learns motion features, and the stream that is shown in gray learns semantic features. Now let's see what goes on here step by step. So first we use FlowNet 3, which is an optical flow network from Thomas Brooks in Freiburg. So we learn optical flow features from 2 consecutive images using FlowNet 3. So we then compute optical flow that's purely caused by the ego motion of the robot or the car here. And on the top of the slide here, you see on the left the optical flow predicted by the network that includes the ego motion. And on the right, you see the optical flow after subtracting the ego motion of the robot. So we then pass these features again through a series of residual units. We basically use the encoder from the AdapNet architecture. This enables us to learn optical flow field features or motion features. So then we have a parallel stream that only takes the current frame as input. And here we exactly have the same AdapNet++ encoder. So this learns now semantic features. And here then we do some complicated steps. So what we do is that we first transform the optical flow into a representation where the edges of the objects are more enhanced. So as you can see on the left here, you see the optical flow from FlowNet 3. And on the right, you can see a transformed version of optical flow where edges of the objects are more prominent. And we call this basically edge enhanced flow. And we use this edge enhanced flow to basically warp semantic features from the previous frame into the current frame. And we fuse these warped features using our dynamic model adaptation unit here. So what this does is that by warping semantic features from the previous frame into the current frame, we hope to instill temporal consistency in learning semantics. So on the decoder side, we again employ our AdapNet++ decoder here, and we get the semantic output on one side of the network. And on the other side, we again use the same AdapNet++ decoder, and we get the objects that are segmented that are only moving. Here we once again we fuse the semantic encoder features into the optical flow field features, once again using a SSMA module here, which is the dynamic model adaptation that we also used for multimodal fusion. And we then pass this through our encoder, and the orange basically pixels denote what cars are moving in the scene. All right, so we evaluated this on 3 standard benchmarks: Cityscapes, Kitty Motion, which is a subset of Kitty that has moving object annotations, and Apolloscape Motion, as well as in data that was captured in Freiburg. And here you can see some qualitative results in these 3 data sets where static cars are basically denoted in blue pixels and moving cars are denoted in orange pixels. And as you can see, we are able to reliably estimate both these tasks jointly. So now the more interesting aspect of this is that by just learning these 2 tasks jointly, there's no more new thing in the network other than learning them together, right? Because we use the same architectural components as the single semantic segmentation network here, that we substantially improve the semantic performance on state-of-the-art benchmarks. So here we show you the improvement in learning the semantics. If I can figure out where my mouse is. So here, that's the improvement in semantics by just learning semantic segmentation and motion estimation jointly. And we further show that warping of these features using temporal warping that I briefly described further improves semantic segmentation by around 1.5%. And you might think, okay, what 1.5% is not so much, but actually once you go towards the higher end of the spectrum, when your model is, nearing the maximum accuracy you can get on a benchmark, 1.5% is a lot in terms of benchmarking case. So on the bottom, you see a plot here where we show you the motion estimation performance. So the motion estimation performance, if you only do segmentation using optical flow, here you can see on 3 different data sets. And then the next on blue, the blue bar shows you the motion estimation. If you use optical flow field features after this, basically the subtraction of the ego motion that I described. So we get a little bit of better performance, and you see a substantially more higher performance after we fuse semantic features into the motion estimation. So this shows you that basically learning these two tasks are mutually beneficial, and it's not only mutually beneficial, but we can also get much more compact models by learning them together. So let's look at some qualitative results. Here you can see results on the cityscapes. So I don't know if you just noticed that, but the car just changed color from blue to orange. When the car was static, it was blue. And as soon as it started moving, it changed color. So on the left, you can see the input images. On the middle, you can see the optical flow. And on the right, you can see optical flow after subtracting the ego motion of the robot. All right, so there's one more part, but let's see what our takeaways are so far. So we spoke about deep learning techniques that enable robots to reliably perceive, understand, and also localize themselves in the environment. We've seen that dynamically adapting the fusion of features in both a multimodal setting and a multitask setting can improve the performance of these models. And we've also seen that learning multiple complementary tasks in a joint framework can be mutually beneficial, both in terms of performance as well as the scalability of these models. Now, these models have significantly exceeded the state of the art on the benchmarks. And not only that, but they've been used on real world robots in diverse environments and operating conditions. And these have enabled also new directions of research that have brought us closer to having real world robots operate more reliably in real world environments. So now the architectures, these architectures that I've just spoke about today, similar to most extensively used architectures, are trained in a supervised manner, which means that they require input-output pairs. So we can only move forward and alleviate this problem by learning without labels. So the last part of this talk basically deals with how can we learn with less labels as possible. So before that, maybe are there any questions on the previous part? All right. Okay, so let's look at some search for some motivation. So if we look at how babies learn, so a lot of the cognitive abilities in babies, let's say in the first 10 months, when babies pretty much cannot do anything, is learned by just observing the world around them. So they amass an enormous amount of background knowledge about how the world works by just watching. And this is why in the video on the top here, you see babies getting surprised when they get air on their faces, or when they see these toys jump, when they see shadows, and so on. But then if you do the same thing to babies that are over 10 months old, you'll see that they will just like shrug, and they will not surprised anymore because they've understood these concepts by then. Well, over the 10-month period, a lot of the learning is more embodied in nature, which means that the learning is more by active physical interaction or active exploration of the world. That's why in the video on the bottom, you see babies often put objects in their mouths, they throw objects, and by doing these actions, they get signals in the proprioceptive sense, in the sense that what action the baby wanted to do and what outcome that the baby sees with his or her eyes, so on and so forth. And with these experiments, they are building a model of themselves, they're building a model of the world around them, and so on. So one of the challenges that we are really excited here in my lab currently is how can we exploit some of these intuition or the features to scale up learning and to enable these models to learn faster and also generalize to real world scenarios. I forgot to talk about one more aspect, which means that after the 14-month period, most of the learning is using language, which means that um, once we learn how to speak, also how we perceive and how we learn actions also depends a lot on language. But I want to talk about that in this talk today. So one of the ways in which we might achieve a lot of background knowledge about the world is by self-supervised learning by interaction or demonstration. So self-supervised learning, you can think of self-supervised learning as a subset of unsupervised learning where the data itself provides the supervision. And as we want robots to learn to perform a many wide range of tasks in diverse scenarios, it's not really practical to ask humans to label every aspect of every new scene and precisely label continuous dimensions either. So instead, what we want to do is we want our models to discover and disentangle the abstract dimensions that matter without explicit supervision. So there are many signals in the world that are free to exploit and that can be used for self-teaching, such as time, viewpoint, depth, tactile, audio, intrinsic motivation, imitation, and so on. And for learning continuous control, we can also learn a policy using a dynamics model or by reinforcing signals using a self-supervised manner by interacting with the environment. So this brings us to the last part. So this is some very recent work um, by one of our PhD students, Yannick here. So in this work, what we wanted to do is that we wanted to enable the robot to visually see by just hearing from the environment. So as we spoke about in the first work, visual appearance of terrains drastically change with seasons and lighting changes and so on. But we want the robot to automatically learn about terrain traversability properties without labels and also robustly in each of these conditions. So the goal here is to reliably classify terrains pixel-wise for safe and efficient navigation. So the idea that we had here was to basically equip the robot with a microphone. You can see our Obelix robot here. Once again, the microphone is pretty much close to the wheels of the robot. And then we have a camera which enables the robot to see here a patch of terrain that is in front of it. So in the visualization that you see here, basically you can see the patch of terrain that the robot sees right in front of it and the path that is traversed by the robot behind, which is basically, you can imagine it as a trail. So what we want to do here is we want to leverage labels from the audio classifier for self-supervising the visual classifier. So I would say the easiest way to think of this is that, let's say that you are looking at this patch of ground, the robot's looking at this patch of ground. So at some point of time, if the robot is randomly navigating in the environment, it will go to this point. So once it goes to this point, then it can use its audio classifier to determine what the patch of terrain is. And you can use this label to then teach the visual classifier. So basically, we want to leverage labels from the audio classifier for self-supervising the visual classifier. But hold on. So here you're going to ask, but we still need labels for the audio classifier, right? So we also proposed the unsupervised audio classification approach. So the way that the whole self-supervised approach works at a high level. So let's imagine we have the trajectory of the robot. So the camera images that we get are first projected into the bird's eye view perspective. So what you see here are, let me find the mouse. So what you see here are the bird's eye view projection of the camera images. And we can do this if we have the pose of the robot and also if the camera is calibrated to the robot. So once we have the bird's eye view, we use an unsupervised clustering approach that uses both audio clips from the recorded terrain traversals and the corresponding patch of terrain recorded with the camera. And we embed each clip in the audio stream into an embedding space. And we use this embedding space to then teach the visual classifier. So the way that we do that is that we cluster the audio embeddings and use the cluster indices basically as labels for the self-supervised visual classification. And these images serve as weakly labeled training data for training the semantic segmentation model in a pixel-wise manner. So what is weakly labeled? So because we can only get labels for the area that a robot has traversed, so it cannot be for every part of the environment, right? So what you see here is that the path of or patch of ground that the robot has traveled and the patch of ground that we get what the label is from the audio classifier. So the colors here denote basically what each terrain is. So now we use these weakly supervised labels for semantic segmentation. So we leverage the visual properties of the patch of terrain that's traversed by the robot. So as seen now from the onboard camera. So now the corresponding audio samples are selected by selecting the audio clip that was recorded when the robot traversed the respective basically patch of ground. So we used here a triplet loss that enforces that the embeddings of the basically the audio clips of the same label are closer together, and the embeddings that are from samples of different audio clips are pushed away. And by using this triplet loss, we basically cluster these audio embeddings, and we also observe that the closest neighbor in the visual embedding space is likely to belong to the same ground truth class as the anchor sample. So therefore, we select samples while evaluation that is closest in the visual embedding space as a positive sample, and we use a negative sample by sampling that are from, let's say, a different cluster in the visual embeddings. So finally, we perform k-means clustering to separate the audio embeddings into different clusters, which basically correspond to different terrain classes. And we use these clusters for labeling the visual embedding. I hope this was clear. So if we visualize how this progresses while training, because this is self-supervised training, you can imagine that we just let the robot randomly roam around in the environment, and it's training continuously while this happens. So at epoch 0, when you basically don't know much about different types of terrains, you see here basically the TSNE visualizations of audio embeddings using the unsupervised approach. So basically at epoch 0, when you pretty much don't know anything about the samples in the environment, you can see the clusters are not very separated. And as the robot explores more and more, it gathers more data, you can see that the clusters are much more better clustered to represent each of the different classes here. So let's look at some qualitative results. So on the left column here, so there are basically two sections. One is if you only have weakly labeled data, meaning you don't have annotations for the entire image, but similar to the image that I previously showed, where you have sparse annotations and where you have full annotation. So we evaluate two different scenarios, and we compare it with a fully supervised approach that is trained in a supervised manner using the weak labels, and our self-supervised approach. And this is using the same supervised approach, the network that we use, but without self-supervision. So the comparison that you should be making is with label data and with self-supervision. And as you can see, without telling what the ground truth labels are, we achieve very close performance to fully supervised learning. And this is using weak labels. And we substantially improve over the previous self-supervised learning approach that exists. And here you see, now imagine that we have, labels for each pixel in an image, right? So if we have not the sparse labels like how I showed you before, but if we have dense labels for each pixel, now we can get a model even more closer to fully supervised learning here. And the difference is basically around 2.5%. But imagine this is like without any label data at all. So let's look at some results. So here we can see some qualitative results. Here you can see different colors based on what the terrain patches are, because where we have grass mixed with different terrains, you see also noisy sort of segmentation. And here we have asphalt, gravel, parking lot, grass, and cobblestone. And so we have, I think, over 12 hours of both audio and video data, which is available on this website if you're interested. It's deepterrain.cs.unifreiburg.de. So what can we do with this, right? So what can we do for robotics is that we can build traversability maps, and we can use these traversability maps for planning paths more efficiently for mobile robots and more intelligently. And more importantly, if you use it in this self-supervised learning framework, we can only imagine that the performance of the model gets better and better. So we do some experiments where we show in the paper that, let's say with 12 hours of data of randomly exploring the environment, a model performance is this much. And then, for example, let's say half a day of data, or little more than half a day of data, you can see that the model still keeps continuously improving the performance. And with this, we can then plan paths such that, let's say we want to maximize traversal time, so we only want to go on terrains that are like asphalt, for example, and not grass. So we can start doing planning and online active learning as well. So that brings us to the end of my talk today. And so for all the stuff I think I presented today, there is like data sets and code, which you can find on the website. Thank you for your attention. Yeah.
Okay.
There are lots of questions.
So yes. So do we have questions? Let's get some questions on the YouTube chat. Okay, we have some. Please, guys, start posting more questions if you have. First question is the number of cluster chosen by some algorithm, or is it chosen by the programmer?
The number of clusters is chosen by the programmer. So if you don't know the number of clusters, then you basically cannot you basically will start going into the domain of continual learning, and that becomes a far more complex problem. So if you really want to do lifelong learning, I think that's the next step to do. Like, you need to start going into the continual learning direction, where you don't know how many clusters you might have in the real world, and then you start getting into more complex problems. Like, for example, one of the problems is called catastrophic forgetting, which is like, if you learned something before and now you're asking the model to learn something new in addition to what's learning before, it's going to forget what it learned before. So those kind of problems start creeping in if you don't know, what are the total number that you expect your model to learn. In this case, we assume that we know that we only want to learn, say, 5 different classes in the environment.
Okay, thank you. So we have another question, which is, are there any open data sets on terrain sounds?
We have our data sets. That's the only one that I know about, which has both sounds, poses of the robot, as well as visual videos. It's basically like video streams. And that's what we used for this last work. That's available online. I think the website is this, deepterrain.cs.uni-freiburg.de. Or if you also go to the lab's website, I think there is a datasets page where you can also find the website, the dataset.
Okay. then we have another question, which is there some method for robust segmentation based on only one camera?
Well, the limitation of camera robust segmentation, I mean, that's kind of the limitation of like cameras, right? So every segmentation algorithm, if you use only visual images, there's only that much that you can do.
Yeah,
What
so he specified he meant without using depth information.
so normal segmentation, right?
Yeah, yeah.
So as far as I know, normal segmentation approaches don't really focus on robustness because, I mean, if you have corrupted input data, then you can't leverage that much to make it uncorrupted. So, and here corruption could mean like a bad lighting change, or it could mean like leaves on the ground. So basically, if you cannot see without the disturbance, then you cannot achieve robustness. So I think another way to say that would be all the RGB based segmentation approach try to segment the model as best as possible um, in the scenario, but they don't really focus on how to improve the perception, because if something is bad in the image, then your model cannot learn anything new about it.
Okay. So we have another question, which is: are there any reinforcement learning approaches for visual navigation?
Reinforcement. There are lots of reinforcement learning approaches for visual navigation. So it depends what kind of visual navigation. So there are, for example, approaches where I think one of the PhD students did using only depth images for navigation. So one of the problems with reinforcement learning is the transfer from simulation to real world, right? So I think in this case, what she did was take depth images as the input to your learning agent or your network to get the features, which is then used by your learning agent. So if you use depth images, it's more like an intermediate modality. Depth or geometry in simulation could be made quite similar to geometry in the real world. So that's some work that transfers to the real world much more better. But there are numerous reinforcement learning works. There's a lot from Silvio Salvarasi's group in Stanford, who does visual navigation with images. There's also some work from Vladan Colton from Intel in outdoor visual navigation using RL. Yeah.
Okay, so we have another question, which is this approach suitable or transferable to aerial image segmentation?
Yeah. So there is no principle, I think, that is different for aerial images. It's the same. So for example, like we do the top-down like projection segmentation in this last work. So it's pretty much the same as aerial or satellite imagery. So I think some people have also used the same paper to win the second place in the NASA challenge for aerial segmentation last year. I just saw it in the people who have cited the paper. So I think it's directly transferable to any type of segmentation. I know people have also used it for biomedical segmentation, for segmenting like tumors and so on. Yeah.
Okay, so thank you very much. We have
Thank
our
you.
audience who appreciated a lot your presentation and the talk. Everybody is commenting on it was very interesting, very inspiring for future projects. And let me actually thank you again and say that I hope this collaboration continues, and also maybe some of these students can I don't know, they are last year master students, so maybe they can do some thesis work, maybe in
Yeah,
collaboration
definitely.
between the two of us, for example.
Mhm. Yeah, definitely.
Okay, Then that's it
Right.
for today.
Yeah,
Thank you very much again, Abhinav. And guys,
thank you.
we'll meet again for the next class. Thank you very much.
All right.